Hi guys, happy St. Patrick's Day. Hope you're doing well. This is going to be my first video. Hopefully you guys did well with your ELA stuff yesterday. They got to be our guinea pigs. They had to go first on Monday. So here I am in my kitchen. You can see my lovely refrigerator back there and my living room and the pantry and the empty milk carton that's on the counter back there. So this is me making my first video. All right, so today we are going to be talking about converting polar things to complex. So we're going to do a little quick review of complex numbers, and then we'll talk about how we can take polar stuff and convert it into complex. So if you remember, I know it's been crazy, you probably are like, what are we even doing? But we started the polar unit, we did all the graphing, right? And then last week with Ms. Curtis, you guys talked about how to convert from polar to rectangular and back and forth. So you guys did just a single coordinate point, converting from polar to rectangular and rectangular to polar, and then you did the entire equation from one to the other. So we're still sort of working on converting different things, but now we're talking about throwing complex numbers into the mix. So I'm going to do a quick little review of complex numbers, talk about how to graph them. We're not really going to spend a lot of time on the graphing. You just kind of need to have a visual for that, for the little piece that we are going to use for the stuff later on. So I'm going to turn my document camera on and give you guys some notes. Hopefully you guys will be able to see this. Please, when you watch this, if it's awful, let me know. Give me some feedback. I'm going to be using pen to give you guys your notes, which I can't stand, but I think that it'll be easier to see than the pencil. So we'll see how it goes. Hopefully if I make any mistakes, I'll just cross through and keep on going. But bear with me. I'm going to get my, oh no, I don't want to do that. I want to share my document camera with you guys. And hopefully you guys can see me. Okay, so we are going to start off with just the idea of a complex number. All right, so you guys have done these in the past, and I'm going to take this off. This is bothering me. My head is starting to sweat. Okay, so you guys have done complex numbers in the past. Complex number is basically made up of two things, two parts. It has a real part and an imaginary part. So we usually will write complex numbers like this. We'll do like A plus BI, or maybe A minus BI. The A and the B can be positive or negative. It doesn't matter. They're just numbers. And then the I obviously is the imaginary part. So we have the A, which is the real part, and we have the BI, which is the imaginary part. Okay, so we have real part, we have the imaginary part. Sometimes complex numbers are referred to as just Z. So we're going to use that in just a second for something that we're going to do. So this whole thing we can call Z. So I don't know if you guys have done graphing with these in the past. Probably not. I don't know that a lot of teachers do that. You usually talk about how to add them together and subtract them and multiply them and all that, but you never really like talk about graphing. So the graphing for a complex number works similarly to graphing just a regular point. So we would take the A and the B, whatever these two numbers are, and you'd put those together, and that would sort of become your point. So instead of having like an x-axis and a y-axis like we normally have when we graph, we have a real axis, and then you would have the imaginary axis. Like that. And so then you would kind of look at your number and you would say, okay, this is my A, this is my B. I'm going to put those together and that's going to be the point that I plot. So even though it looks like it's made up of two different pieces, when you plot it, it's still just a point, just like any other thing that you would graph. So if we had, let's say that was our point. So the coordinates of that point are A and B. So I'm getting the A and B from up here. Right? So it's just like any other point that you plot. You go over a certain distance, that's our A, and then we go up or down a certain distance on our other axis. So in this case, that would be our B. And then this distance, the distance back to the origin, that is our magnitude, okay? But in complex terms, that's called the absolute value of a complex number. So the distance, so absolute value of a complex number, absolute value of a complex number, it's the distance, I'm kind of running out of room here, distance from 0 on the complex plane. Distance from 0 on the complex plane. You know what? I'm gonna see if I can hide myself. There we go. So this distance, that's what we call the absolute value of a complex number. So the way that we denote that is we do Z, and again, Z is just the way that we represent this entire number up here. So when you see this Z, you can think A plus BI. So we put little absolute value bars around it. So this is saying that I'm finding the absolute value of a complex number. And the way that we do that, we can also write it as the absolute value of A plus BI, either way. And then the way it's calculated is kind of what you would expect, right? If we look up here, just like almost everything we've done this year, it involves some kind of a right triangle, right? So if I wanted to find the length of this, this is essentially just Pythagorean theorem. So we would do A squared plus B squared, and then we'd have to take the square root of it. So that's our formula for how we're going to find this distance, the absolute value of that complex number, okay? So the first couple of examples I'm going to do, I'm going to take a couple and I'm going to graph it, and then we're going to calculate that absolute value, okay? Slide this up. All right, so example 1. So let's say we have Z equals 4 plus 3i. So that's our complex number. We want to graph it and we want to find its absolute value. So graph. Remember, this is the real axis. This is the imaginary. And I'm just going to take my two values. This is my A, this is my B. So I'm going to go over 4, 1, 2, 3, 4 on the real axis, and then up 1, 2, 3. And plot that point. And then our absolute value is our distance back to the origin. So if I want to calculate that, we know this distance was 4, and we know this distance was 3. So if I want to calculate my absolute value, I'm going to do 4 squared plus 3 squared. So hopefully You can do that one in your head, right? That's just a 3, 4, 5 triangle. So that one hopefully is one that you kind of have memorized at this point. But if you work it out, it really does come out. You're going to get 16 plus 9, which is the square root of 25, which is 5. Okay. Oops, kind of went off the page. There we go. So it really does work out to be 5. And again, it's a distance, right? Up here in the definition, we said absolute value, distance from 0. So we don't have to worry about like a negative or anything like that. If we're treating it as a distance, it's always going to be positive. All right, so let's do another one. Example 2. Let me see, I've got some with negatives in there. So let's see, we've got -2 minus I. So if I want to graph that, remember this is real, this is imaginary. So I've got -2 and -1. So I'm going to go over 2 on the real axis and down 1. There's my point. So we could actually go back and label these if you want. So I could go back and say this is the point 4 plus 3i. And this is the point -2 minus I. And then we would do the absolute value the same way. So I've got to do -2 squared. I've got a -1 squared. And then square root over the whole thing. So this is going to be 4. This is going to be 1. So the square root of 5. That's my absolute value. That's the distance right here back to the origin. Okay? All right. So we kind of hopefully remember absolute, or not absolute value, complex numbers. Hopefully that gives you a little refresher. This stuff you probably haven't done before, but hopefully you do remember, like, you know, that it's got these 2 parts to it up here. All right, so the next thing that we're going to talk about, my page here, is how to convert our polar stuff that we've been learning about to complex form and then back and forth, okay? So the first thing that we're gonna do is talk about converting from complex to polar. Okay, so the first thing that we need to know is that the polar form of a complex number, so we know already that if it's a complex number, it's going to have some imaginary stuff in it somewhere, right? So even when we have a complex number and we want to put it into a different form, into a polar form, because it's a complex number, it's still going to have imaginary stuff in it, okay? And then polar, if you think about when we were plotting the polar points, we had a certain distance that we would go out from the origin. That was like our R value, but we also had an angle, right? So if it's a polar form of a complex number, we're probably still going to have that angle in there. And then we are going to have some imaginary stuff. So polar form of a complex number is given by z equals, so again, we're calling it z because it's a complex number. So that z just tells us, that's just kind of a really standard way of saying, oh, hey, we've got a complex number. So z equals r, so there's the r that we've been looking at, and then we are going to have in parentheses cosine theta plus I sine theta. So r and then cosine theta plus I times sine theta. And then we have to know how to find r and theta, because when we actually write the complex number out, like when we do one in a second that's going to have some actual numbers in it when we get to the examples, the r value, instead of an r, there's going to be a number there, right? So we have to figure out a number value for r, and then we have to figure out what angle we're supposed to put here and here. Okay, and so we have to do a little work to figure out r and to figure out theta, and when we get those, we just plug them into this form. Make sense? So we have this, the polar form is given by this, so it's going to look like this, but then we have some more to add here, where r equals that absolute value that we were finding a second ago. Which was this little formula that we were just using on our previous examples. So hopefully that makes sense to you, right? Because when we graphed those points a minute ago, this little calculation, we were finding the distance from the origin, right? If I flip back, we were finding this distance. So I could even go back and label it. This is the absolute value, right? It's the distance from the origin. Well, if we think about what we were doing with our polar graphing, that's kind of the same thing, right? The r value was how far out are we moving from the origin, or how far out are we going from the pole? Once we found the right angle that we needed, we found our angle, and then we would go out so many rings on our graph, right? So it should make sense to you that the r value and this absolute value of z kind of measure the same thing, right? We're starting and we're measuring out from the origin or from the pole. So hopefully it makes sense that those two things kind of go along together. So that's how we're going to find the r value that's going to go here. And then we also need a way to find our angle. Okay, we also need a way to find our angle that's going to go here and here. But again, if we look back at our picture that we just drew, sorry, I'm flipping back and forth so much. If we look at our picture that we just drew, we have this right triangle, right? So the angle that we're looking for is here. So we're probably going to find that the same way we've been doing it all year, right? If we need to know this angle, and we know our two sides, then we're going to do probably some sort of tangent, like inverse tangent thing, to solve for that angle. So that's exactly what we're going to do here. So our r value is basically just our absolute value that we learned a second ago. And then the angle that we need is going to be doing the inverse tangent of b over a. Because normally when we do inverse tangent, remember we do y over x, or we do the vertical over the horizontal. So we're still doing that. We've just given our vertical and horizontal different names now. Instead of calling them x and y, we're calling them a and b, because that's kind of the convention we use for complex numbers. But we're still doing kind of the same thing that we've done plenty of other times to find that missing angle. We're doing our inverse tangent. So give you a little bit of vocabulary. R is called a modulus, and I have to look and see how to spell this. Modulus. And theta is called the argument. You don't really need to know those. Throwing that little bit of vocabulary out at you, you probably won't ever hear me mention that ever again. But you can sound fancy if you want to say, oh, this is the modulus, and oh, this is the argument. I'm probably never going to use those words again. I'm just going to say r and theta. But we'll throw that in there. All right, so let's do an example of converting something that's a complex number into a complex number that's in polar form. So we're going to start with something that just looks like a plus bi, like we were using a second ago, but we're going to convert it, and when we're done, it's going to look like this, except we're going to have a number here for r, and we're going to have numbers here for theta. Sound good? All right, so let's do it. We've got example, I don't know what we're up to. I think example 3 for this one. So my complex number is -6 plus 8i, right? -6 plus 8i. So if I wanted to, I could graph that point just like we were doing a second ago. We don't really have to graph it here. We're more concerned about converting it into this like new form up here. So in order to do that, I need to know 2 things. I need to know the r value, and I need to know my theta. I need to know my angle. So we got to find these 2 things and then plug them into this guy up here. So let's find our, we'll call this r. So we'll find our modulus. Ooh, see, I lied. I said it again. I told you I wasn't going to say it. I said it. -6 squared, and then 8 squared. So I'm going to try not to run off the page here. So 36 and 64. That's going to make 100. So square root of 100, we're going to get 10. So our r value is 10. And then I need to find my theta. So this is one of the ones where we are going to have to think a little bit, I believe. I'll have to go back and look at this again as I'm working through it. But if we do our inverse tangent of 8 over -6, and I believe, let me see here. Are we in, it looks like we're in radians. I don't know if it, does it matter which one we're going to be in? I think it matters. Let's do this. Let me get my calculator. Let's do this in degrees. Let me see what mode I'm in. I'm going to switch my mode. Okay, so if I do inverse tangent of 8 divided by -6, I get -53.13. But let's think about this. -53.13. This is another one of those places. I know this is your favorite thing in the world. This is one of those things where we have to stop and think, is this the angle that we really want? Because remember how our whole like restrictions go with inverse tangent and inverse sine and all that. So this is giving us an angle that is down here in this quadrant, right? If I start here and I go -53 degrees, I'm going to go in this direction, 53 degrees. So that's where I am based on this answer. But where am I supposed to be based on this original point? Think about where this is. I told you we weren't going to have to graph it. Maybe we do. Maybe we do need to think about where it is. -6 plus 8i. I would go 6 in this direction and then up. So my point is actually up here in this quadrant, right? My calculator is giving me an angle down here. So this is one of those times when we got to go whoop, and we got to like switch it. We got to flip it around the other way. So that means I'm going to have to add 180 degrees to this. So if I do that, 180, I get 126.87 if we round it. That makes more sense, right? 126 degrees, That's somewhere over here in this quadrant, which is where our original point was. So that makes more sense. So my R value is 10. My angle is 126. And so I have to take those two things and I have to put them into this form right here. So my new number is going to look like this. We've got our R and then parentheses cosine 126.87 plus I'm going off the page over here. Hopefully you guys can see this. 126.87. So this number, this is the complex form of this thing that we started out with. Okay? That's what that means. This is the complex form of this number that we started out with. Okay, I'm going to work through another one. So let's see, I think I got enough room to do it down here. Example 4. Okay, I'm going to work through this one. Let's see, which one do I want to do here? Let's do this one. So we got z equals 4 plus root 3 I. Got a root thrown in. And that I is not under the root. It's not under the root. It's root 3 times my I. So this is my A and this is my B. Now if you want, you can pause the video, work this one out, and then see how you did. Or you can just watch me do it the whole time, whatever you like. Okay, so I need my R, which is really just absolute value of the number. So I've got to do 4 squared. I've got square root of 3 squared. That's going to be 16. Square root of 3 squared is just going to be 3. So this is the square root of 19. Square root of 19. I don't think there's anything we can do with that. We can't break that down anymore. So we just have to leave it like that. Now we got to think about our theta. So we're going to do inverse tangent of root 3 over 4. Root 3 over 4. So let's see. Get my calculator. We're going to do inverse tangent of root 3 over 4. And again, this is in degrees. My calculator's in degree mode. So I got 23.41 degrees. Can you hear my child in the background? He's playing some sort of video game. He's yelling at something. I don't know what's happening. Okay, so we have 23.41 degrees. Okay, so I'm going to stop and I'm going to say, is that where I need to be? Is that angle where I need to be? This is a first quadrant angle. This would also be in the first quadrant. Both of these are positive. So these are both going to, this point would be in the first quadrant. So I don't think I need to do anything to my angle at this point. I can just take those two things and put them into our form that we had up at the top of the page. So I've got root 19, and then I'm going to have cosine 23.41 plus I sine 23.41. And that's it. We're just going to leave it like that. I suppose you could, because all of these are just numbers, right? Like you could actually type into your calculator cosine of 23.1. You could get a number. You could do the same thing with this. You could get a number. Then if we wanted to, we could distribute root 19 through all of that. But then that would turn it back into what we started. That's actually the next thing that we're going to do. So if you're sort of wondering why is she not doing that? Why are we just stopping here? And we're not like, distributing anything. We're not figuring out this cosine or this sine. If we did that, we would actually end up back here, okay? So that's how you go the other way. That's the last thing I'm going to show you. If we start out with something that looks like this, and we wanted to turn it back into that, how would we do that? Well, the easiest way is just to like work all this stuff out, right? So that's going to be our last little bit for this particular video. So this is like a new heading, converting polar to complex. So what we're going to do underneath this, I'm going to say that we're going to evaluate in order to return to what I'm going to call regular complex. So regular complex is this, just the normal A plus BI. Polar complex is that big thing that we were just looking at with the R and the cosine theta and the sine theta. Regular complex is just this. So now we're going to start with something that's that big, ugly mess that we just had with the R and the theta, and we're going to turn it back into regular complex. And again, the way we do that is we just kind of like go through and we just evaluate everything, right? We just like do the cosine and we do the sine and we distribute the R and everything through. And when we do that, we end up with something that's in this form. All right, so let's do a couple of those. So I don't know what example number we're up to. Let's see what we have, 4, 5. All right, example 5. All right, we're gonna do 2 of these. So, and again, we're starting with something that's in that big form that we just had. So plus I sine 30. So we're going to take this and we're just going to turn it back into kind of regular complex form, okay? So let's think about this. This is stuff that we know. I'm going to bring my 2 down. Cosine of 30 degrees, cosine should be root 3 over 2. And then the sine of 30 degrees, 1/2. So remember these two, this I and this 1/2, they're kind of like multiplied together, right? So if you would rather put the I on the other side, you can do that. You can say 1/2 I. That's kind of how we're going to write it at the end anyway, because if you look back up here, usually the I comes at the end, right? So if you want to go ahead and make that switch, you can. So now what I'm going to do is I'm going to distribute my 2. So the 2's are going to cancel here, and we're just going to have root 3. And then 2 times 1/2, it's just 1. So this is just going to be plus I. And that's it. We've turned it back into sort of just our normal A plus BI form. Okay. All right, last one. Example 6. So let's see. Let's do this one. Let's do 4 cosine 5 pi over 3 plus I sine 5 pi over 3. All right, so again, hopefully we remember some of this stuff from our unit circle. So 5 pi over 3, that's going to be, let's see, 3, 4, 5. That's going to be in kind of the 4th quadrant. So cosine of 5 pi over 3 is 1/2. The sine of 5 pi over 3 because it's down in the fourth quadrant, so sine is going to be negative. It's going to be negative root 3 over 2. So now if we distribute our 4 times a half is 2. And then I'm going to remember that this is a negative sign here, so this is going to be minus. When I distribute my 4 here, this 2 can simplify a little bit with this 4. That's going to be minus 2 root 3, and then my I on the end. So there you have it. So that's kind of the easiest of the bunch, right? Unless, you know, you don't remember your unit circle stuff, but I know everybody does, so we don't have to worry about that. But that's kind of the easiest of the bunch, right? We didn't have to go off and find an R value or an angle or anything. We just had to take what was there and just kind of work it out and evaluate it and simplify it as much as we can. All right, let's see if I can bring my video back up. You know what? Let's see. I'm gonna stop sharing that. There I am. I'm back. Yay. Okay, so I hope that wasn't completely overwhelming. I felt like I was sort of rambling on and on and on. It's very different from you guys asking me questions along the way and stopping and starting. So that was a whole big stretch of me just talking. So hopefully you can, as we move forward, you guys can kind of pause this and work out the example and then unpause it and check to see how you did. I'm going to also probably post some kind of a worksheet, probably just like a CUDA sheet that's got some practice of converting back and forth, maybe a little bit of the graphing practice that we did at the beginning. And then we will go from there. So we've got one more probably big topic that I'll do a video on for next week, and that's going to finish out this polar unit. So still don't really know what the deal is going to be with assessments, but hopefully you saw my email that I sent out on Sunday about just saving all of your work. They've been saying in a bunch of emails that I've read that you guys will have, when we go back, you'll have like 2 weeks to get all of your stuff in. I don't know if every single bit of it will be graded. Hopefully yes, or you know, it might just be like how I normally do homework, where you know some of it gets checked and some of it doesn't. But I haven't heard any updates on assessments, but as soon as I hear anything, I will let you guys know if that's something that they think we can do virtually. I don't know. One of the things that I would like to try to do is use a site called Flipgrid. I know some of you may have used that, but you guys make little videos and send them to me. So it's kind of like Desmos in the sense that I would give you a code. You would go to the site. I think there's probably an app for your phone. And I would give you a little code and you would log in with the code to our little, or your little class. Like I would have a second period group and a first period group and whatever. And then I would give you a topic or a problem and you guys would make a little video talking about how to solve it. And then you could send me those and I can kind of watch those and give you feedback and give you, you know, some sort of homework grade or something. I don't know what the best way would be to do to check homework. If you guys have ideas, please let me know. If there's, you know, something that another teacher is doing for homework. Math is a little bit different in the sense that, like, you know, I got to just see that you've worked it out. So I know, you know, sometimes you guys, if you're out, you are absent, you send me pictures of things, which is totally fine. I don't know the best way to do that right now because, you know, I'm going to get 85 emails of pictures of your homework. I don't know how to deal with that. But if we did Flipgrid, I would have 85 little videos that I have to watch. So I don't know. I don't know the best way to do it at this point. It might just be a thing where I'm not checking it along the way. You just sort of like hold on to it, drop my pen, and you know, we figure something out at the end of all this. So yeah, I miss you guys. Hopefully you're doing really well. I know you're gonna keep up as best you can. So yeah, that's that. Happy St. Patrick's Day. And I will see you next week. I'm going to have office hours, and maybe we can chat a little bit if you guys have questions. Okay, that's it from me.